So this video is going to be covering exponents, perfect squares, and square roots. We're going to chop it into a few different sections. All these three items tie into each other. So first we're going to talk about exponents. You can represent an exponent in three different ways. You can express it in exponential form. That's when you have a base number, that's always the big number, and then the little guy is known as the exponent. And there's your exponent. So base to exponent, you'd read that as 3 to the power of 2, or you could say 3 squared. Expanded form is the longer way of writing 3 to the second power. That really just means 3 times 3. And then the simplified form is going to be 3 times 3, which works out to 9. So that's the simplified form. These are the three different ways you'll see when dealing with exponents. Let's do another one. Excuse me. So we have 2 to the power of 3. You'll also hear it as 2 to the third or 2 cubed. So once again we have 2 as our base, our 3 as our exponent. And we're going to expand this, write it out in long ways. The long form using its factors, factors being numbers being multiplied. 2 times 2 times 2. If you had a calculator, you'd punch the 2 button 3 times. This is going to work out to 2 times 2 is 4 times another 2 is 8. Don't make the mistake of just doing 2 times 3 is 6. It's not going to be 6. Alright, let's go ahead and try these out. You can pause the video, work these out on your own, think them through. So hopefully now you've paused. This first one over here, 5 to the second power, or 5 squared, that is going to be 5 times 5, which works out to 25. So we're simplifying each expression. These are all considered expressions. These are all numbers and operations, just written in a new way. So the next one, 2 to the power of 4. You'd write out 4 2's. You don't have to do this part, but it really, for what we're doing right now, this is what 2 to the power of 4 means. You can go straight to the answer and get 16. These 2 2's make a 4, these 2 2's make a 4. 4 times 4 gives you 16. All right, 1 to the power of 5. A lot of kids are going to say that the answer is 5. It's not 5 because our base number is 1. That's the number that's going to keep repeating. And it's going to be 5 of those 1's. And that works out to just 1. So 1 to the millionth power would have been 1. 3 to the power of 3, you're going to write it out 3 3's, and that works out to 27. Is this equation true? Is 3 to the second equal to 2 to the third? Pause it and think about it if you'd like. If you wrote these out, you'd write it out as 3 times 3. Over here you'd have 3 2's. This works out to 9. This works out to 8. They're not equal. So 3 to the second is not equal to 2 to the third. So just be aware that an equal sign by itself means equals, but with the slash means it's not equal. Let's go ahead and try another one here. 4 to the power of 1. Is that equal to 1 to the power of 4? Well, it'll just be 1 4 over here. That'd be 4 1's. That's where you got to be careful. And then you get a 1 over here. So they're not equal. This equation's not true. Okay, perfect squares is what we're talking about next. Perfect squares. What is a perfect square? A perfect square is a number that is the product of two equal factors. Product meaning the result of multiplying, and factors meaning you're multiplying the same thing. Let me show you some examples of this. We've got 1 times 1 equaling 1. We have 2 times 2 equaling 4. 3 times 3 equaling 9. These numbers being multiplied are all equal factors, and then what 1 times 1 is 1, 2 times 2 is 4. These are all perfect squares. Let's continue this. Let's just keep going with the pattern. If we have 4 times 4, 5 times 5, those are all equal factors that we're multiplying, and these are the results of those equal factors being multiplied. These numbers are perfect squares. So of these two choices, which number is a perfect square? I'm going to go ahead and list some of their factors. So we've got 1 times 12. 1 and 12 are both factors. 2 times 6, 3 times 4, and there's nothing else. So this number 12 has 6 factors total. None of them repeat. There's no number times itself that can get you 12. Over here for 16, we've got 1 times 16, we've got 2 times 8, and we have 4 times 4. 16 has a total of 1, 2, 3, 4, 5 factors. And then in this case, we had this one factor multiplied by itself, and that's going to be the reason why 16 is a perfect square. Let's do another one of these. 80 and 81. Some of you might recognize it immediately, but which number is a perfect square? I'm going to go ahead and list some factors of 80. You've got 1 times 80, 2 times 40, 4 times 20, 5 times 16, and 8 times 10. Are any of these factors repeating and multiplying by itself? No. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 factors. None of them repeat. Over here for 81, we have 1 times 81. You could do 3 times 27. You could do 9 times 9, and that's it. We have a total of 1, 2, 3, 4, 5 factors. We don't count this 9 twice. So it has 5 factors, and then this 9 times itself is the reason why we can say that 81 is a perfect square. It has a factor where it's a product of 2 equal factors. We'll do one final one here. 49 and 50. Hopefully you know this one easily. I'm going to list its factors. These are the only factors it has. 1, 2, 3 factors. We have a product of equal factors. I'm going to go ahead and check out 50 though. A lot of kids might say, oh, well, what about 25? 1 times 50. 2 times 25 works, but is 25 being multiplied by itself? And it's not. 5 times 10. There's the 2 equal factors multiplied. There's your product of 2 equal factors. So 49 is the perfect square. I'm going to show you this. This is one quick way of recognizing what the perfect squares are. Perfect squares are products of 2 equal factors. So hey, if we do 1 times 1, we get a 1. 1 is a perfect square. We do 2 times 2, and we get 4. 4 is a perfect square. We do 3 times 3, and we get 9. 9 is a perfect square. 4 times 4, we get 16. Notice how your perfect squares are coming diagonal right down the path here. 5 times 5, 6 times 6. There's a lot of cool patterns you can also notice through perfect squares when you start listing them all. And there you go. We've got all of these are products of 2 equal factors. 10 times 10 giving you 100. For 7th grade math, you need to have memorized the first 20 perfect squares. So we have the first 10 listed here. There's only 10 more you need to know. And we'll mess around more with that in class. Okay, square roots now. Square roots. This is called a radical sign, and this just means what is the square root of a number, or the square root of whatever's inside. So we're going to do a few examples. Solving for square roots. If you have square root of 25, what is that going to work out to? You want to think about it like this. Well, first you'd read it as the square root of 25 equals something. We want to look for a factor of 25 where if you multiply that factor by itself, 2 equal factors, you get 25. So what times itself is 25? A 5. 5 times 5 is 25. So we could put a 5 here. We could also read it as the square root of 25 equals 5. We're going to do another one. Square root of 81 is something. The square root of 81 equals something. What times what is 81? If you really know your times tables, you know that it's going to be 9 times 9. So the square root of 81 is 9. The square root of 81 equals 9. Let's try this one. This one can get tricky, because now we're starting to deal with larger numbers. The square root of 121. The square root of 121 equals something. What times itself is 121? If you're comfortable with numbers, you know that 10 times 10 is 100, so it's going to be fairly close to something times 10. So let's try 11. It does work out. Now this is where eventually you want to just get some memorization going on and just know your first 20 perfect squares. It's going to be 11. The square root of 121 equals 11. Final questions here. The square root of a number will always, sometimes, or never be smaller than the original number. Now this can get tricky. There's a lot of words here. Square root of a number, whatever it works out to, is it going to be smaller or larger, or we don't know, or is it equal to the original number? Let's do some examples. Square root of 36 works out to 6, because 6 times 6 is 36. So the square root of 36 is smaller than 36. Let's try another one. Square root of 100 is going to work out to 10. So the square root of 100 is 10. That's smaller than the original number. So far it looks like it's always going to happen. Well, square root of 1, what times itself is 1? It's going to be 1. So any other number, it's going to be smaller. So we really can say sometimes, but you can almost say always, but with an asterisk here, because that's like a special note. It's always except for the square root of 1. Any other time, your answer, your square root, is going to be smaller than the original number. All right, one more. The square root of 20. Now some kids are going to look at this and go, maybe it's 10. Guys, don't say 10. Don't chop a number in half and think it's the square root. 20 is not a perfect square. So the only thing you can do is maybe do an estimate on what it's between. Or if you have a calculator, you can type in 20 and then hit your radical button. But let's say we didn't have a calculator. So we could realize that, well, 10 times 10 is not equal to 20, so don't say 10. 4 times 4 is 16. That's pretty close to 20. 5 times 5 is going to be 25. So it's going to be somewhere between 4 and 5. And if you had a calculator and typed it in, you'd get 4.4721 going on and on and on forever. And that's called an irrational number. We'll get more into those later on. But for now, you just need to realize this wouldn't work out to a nice number. It would work out to something between 4 and 5. That is about it. I hope this helps. Best of luck to you guys.